Hello everybody. I'm going to now have a talk on how to use Postgres, where some common wisdom would tell you to use some NoSQL or some lesser databases. So basically I'll try to convince you that almost everything you can do with NoSQL can also be done with a real database. So, I'm Hanno Krosing, that's my email, Skype also. Feel free to contact me, ask questions if you later remember something or want to ask more. I've been using Python since forever, same for Linux and PostgreSQL. I used PostgreSQL even before it acquired SQL, so you could claim that it was a NoSQL database then, even though it was a relational database, which many NoSQL databases are not. So I've been hacking and doing minor contributions both to Python and PostgreSQL for about 20 years. There's a little amount of my code in both. My real experience with large databases were when I started as a DBA for Skype. Skype still does most of their, I would say even all of their data manipulation using Python. All their databases are in PostgreSQL. And when we had a need to scale the databases, we first also used Python, and later we abstracted the scaling or partitioning part out into a language called PL proxy, which is an embedded language or a pluggable language for PostgreSQL. And for last few years, 5-6 years, I've been working as a database consultant, mainly on scalability and performance issues at second quadrant. Also, I still occasionally work with Skype founding engineers, investment company, ambient sound investments, evaluating some technical merits of some potential startups, and also doing little work for a Finnish company who tried to do e-invoicing, the same thing that Skype did for free calls. Also, I've written a book about Postgres, so if you want to, this does almost nothing with Python. I'm currently writing another one which has also a chapter on PL Python. So I'm from Estonia, which is a small country from Northern Europe, and the main things Estonia is known by nowadays is that we destroyed Soviet Union and we wrote Skype. Both are things that several others had tried to do before but failed. So let's go now to the main topic. Wikipedia claims in the article about what is a NoSQL that it can be either key value stores, it can be document databases, it can be graph databases, hierarchical databases, basically anything that does not, either they don't use SQL or they are just not classical relational databases. So, and the main expectations that people tend to have about NoSQL databases is that they are scalable. Not all of them are, but many of them are. One of the reasons is that much of the complicated stuff is left out from the database and you have to do it in your client libraries. So scaling a simple key value store, simple database that doesn't need to preserve integrity is much easier. Also, they are expected to be fast. Anything nowadays is expected to be fast, also the SQL databases. And they are often said to be easy to use, which means that first they have been easier to use than SQL databases for the original authors, because everything that you wrote yourself is usually easy to use, or it is well integrated in some client-side libraries, so it's either looks like your native dictionary, native classes, they are automated, all the saving stuff. And they can also be a good fit for a specific domain, so either they are some document databases or media streaming or something else. So when people start their applications, mostly they think that they don't need a database at all. Sometimes they claim that they don't have data, or they say that the data is so simple that they just store everything in file and expect that files are fast. So if you bypass some part and then write the file, then it should be fast, because you are omitting some things, which actually is not so, because the file system is also a database, and often the databases have done a lot of hard work to work well with the shortcomings of the file systems, or they just have a different set of requirements for speed. And most of the classical ACID relational database features are useful when things go wrong, when programs don't work, when you try to insert some wrong shape data. But developers mostly think about how to make things go right. And so all of this extra thing you are forced to think about from the start seems like it's something that's almost not needed, and anyway, you don't want to think about it from the very beginning. But in the end, a large portion, some estimated 80%, some 95%, is about error conditions or things to do, or handling things when they go wrong. The classical relational databases are supposed to have the properties called ACID, which first is atomicity, which means that either all your changes to the database succeed or none of them succeed. For simple writes or simple databases, this is sometimes true. Consistency means that you can set some rules how the data must relate to other parts of data, or what the data represents. This is lacking for simple writing, also for many NoSQL databases. Isolation means that other people can't see your changes before you have done all the changes. This is also something that most NoSQL databases lack. You can sometimes force it by locking, but again this kills performance. And also same about durability, which means that when your write is done, then you should be sure that you actually have the data in the database. Again, this is possible with some write modes, with direct file writes, basically write-through mode, where you make sure that everything is written to disk, but they tend to be slow, especially if you do more than one small write in one transaction or in one database interaction. And so different NoSQL databases also offer different levels of durability. Mostly they do it, there are two things: a single database or single shard durability is done usually by having some kind of write-ahead log, which is also the same thing that most SQL databases do. And then they also provide replication, which means that your data will be be stored on many databases or many instances of the same database. Building everything yourself is okay for simple prototypes, or just when you're exploring your domain. But it's usually not good for larger things. Once you have done your prototyping, you should actually, if you are not planning to develop yet another database, then you should just bite the bullet and use some existing database, be it NoSQL or SQL database. You have to do some parts of yourself by yourself, but the more you can reuse of good components, the better off you are. At Skype, we started our scaling efforts about the same time that Google and Amazon. They ended up with NoSQL databases or large stores. At Skype, we did this based on PostgreSQL, and currently there are more than 1,000 servers working together at Skype, all running PostgreSQL, larger ones having hundreds of shards of the same database. Okay, so why it is easy why should you choose Postgres if you need to develop something? Postgres has a really long history. Lots of smart people have been working on it, and it has the main goal already from the start has been to make it extensible, which means that almost everything can be extended by users by writing some code. You can have user-defined data types, user-defined functions, operators. For example, similar like you have in Python classes, you can define addition or something else. In Python, in Postgres, it's similar. You have plugin languages. It comes already from the core developers who support for Python, Perl, TCL, and there are lots of others that are developed outside. So using any of these, you can do work inside the database, which, as I demonstrate in a moment, really is a powerful thing for all kinds of storage solutions or database stuff. Also, you can have specific indexing methods. It now currently comes out of the box B-tree, several inverted indexes, in the latest version also an index which is called KNN, or K nearest neighbors, which does already inexact searches and returns the matches in order of distance. For example, you want to find nearest pizzerias around here, then you can use this index, and it does not need to get all matching items and then sort them by distance. Already the index is smart enough to only touch a small number of the rows and then return them in order of distance. And so also most other things are not hardwired in Postgres, but they are defined in system tables and thus can be overridden or added to without actually going to hack the C code. Now let's talk about how to do a document database in Postgres. There are some nice examples how people at Heroku did JSON database in Postgres. They used PLv8 for in-database processing and JSON format for storage. The same with the EuroPython looks like this. First you need a validator function, which here it just simply tries to load it using the built-in JSON module. If it loads, it returns true, then if not, it returns false. then you can use this function as a check in creating a domain, and then you use the domain for already as a data type in your table. And once done so, then any string you is a possibility to have it a little smaller. I think it will be kind of hard to follow if parts are off screen. Strange, okay. If I try to make it smaller, then it disappears. Anyway, this way you can define a type in database with some conditions which are always checked when the type is used. And see, if you try to insert something that is not a JSON, valid JSON document, then you get an error. And if it is, then it gets inserted just fine. JSON data type is now added to Postgres 9.2, so soon you don't need to create your own domain in case you want to use JSON. Okay, here is a small function that runs in database and creates JSON documents. Basically reads in the words list to have some realistic looking documents, and then creates a typical schema for some social network or type site. There are users, then the list of users followed by the main user, the user's age, and just to demonstrate that it's not a fixed structure, you have a random key also here. So each record has a different structure. And here I define the helper function inside the database function, and then I prepared an insert query and then used this helper function to actually generate the JSON documents that are inserted into the database. And I used this to insert 10,000 rows. It's not terribly fast. It's about a little less than 1 millisecond per row inserted. Most of it goes actually in JSON formatting and parsing, as we see later. But they are all first generated, then they are converted to JSON, and then for each row also the validation format function runs, which has to decode them once again, so it's not too bad either. Let me get something. Really large instructional code. Okay, now it's at least you see the starting part. It's much better than seeing the middle. So, and here I define an accessor function which gets the age from this JSON document, and then use this function to actually compute the average age of the generated data. Again, as you see, it's not terribly fast. It takes 6 seconds to query just 30,000 documents. but the reason is that currently it doesn't use any indexes because I didn't create any, and so it has to parse and convert all the 30,000 strings to Python structures from JSON representation and then run this function on them. And here is this conversion, JSON loads. It is a Python function that takes a JSON string and then returns Python lists and dictionaries corresponding to this JSON data. Now to make this faster, you can actually as you see, it's full scan, and also it has to run the function each time. But when you add an index, because in Python you can use, in Postgres you can use also functions as base of index, you can have conditional indexes, all other kinds of things, then suddenly it runs in 5 milliseconds instead of 7 seconds. And for most of these kinds of data you can add your own indexes. But even without index it kind of felt a little bit slow. So so the reason is that the JSON module itself is kind of slowish. It's not really slow, but it's also not a native representation or native storage format for Python. So I redid the same thing using Marshall as the storage format. And it's not terribly much faster, but still it's 4 times faster when I store the things in Marshall format. And again, the query without index is about 4 times faster. They look very much the same because the interfaces are the same. Interface is still module name.load_s, module name .dump_s. Okay, and if you want to still to have the thing in JSON format, then it's easy to write a conversion function from Marshall data to JSON data, which says Marshall loads, JSON dumps, and you have a JSON. And next I did some extraction of already put the extraction of users who follow user fireflies, and this again uses some more advanced features of PostgreSQL. This is an array overlap operation, which again can be indexed if you use a special index type gin, and you can put this index type also on a function. So again, this went down from 2 seconds to 41 milliseconds. And not only has it specific index types for interesting things, it can also combine indexes and do other interesting stuff. Also, the gin index is smart enough so that if you want to see two overlapping things, and it can still use one index condition to get things that match both. And here is the runtime is only 0.2 milliseconds to extract this condition. So basic document storage or document databases are quite easy to do, and they are really extensible. And you can And the trick is that you must do your functions inside the database, not try to run them from outside, otherwise the latencies will kill you, and also no indexed things are usable and so on. Okay, and this will be all now about the document storage part. I'll go quickly over how we did the scaling part at Skype. This is not directly to do with Python, but it just shows that it's not really hard to scale if you control your applications, if you have access and control over how the code that interacts with the database is written. First, what modern PostgreSQL on modern hardware is capable of without any scaling. You can load a few hundreds of thousands of rows per second. You can do a few hundreds of thousands of separate select requests per second. And you can do about 10,000-15,000 separate transactions doing simple inserts updates. This needs quite a beefy machine, some 24, 32, maybe 64 cores, but it's still possible to do without resorting to scaling over multiple machines. Okay, that's how I ended up doing things at Skype. So basically I knew the guys who wrote the software. They needed a database, didn't have much money, so they knew that I do Postgres, so I ran some tests, and they were quite content that at that time a few hundreds of users per second could be added when the database was already containing a few tens of millions of users. And then we started growing with some mid-range servers at that time. They had 2 or 4 cores, usually 2. First we did the usual thing, split the databases, then we did horizontal splits, and used trigger-based replication for moving some data between the databases. And basically this is how we split up the database from a single one to having many, and these were already some replications, and also some of the replication was used for actual, not application, but for some processing. For example, we did ensured consistency of balance updates, so that we inserted balance change records and then replayed them on the other side to the real database. So if something failed, then we were able to redo it, so we could be sure that nothing is lost. Yes. And but we saw that we can't continue very long with just functional splitting. We had to start splitting databases, single database tables, and which is currently referred quite often as sharding when you split up one database. And we had a very fortunate decision for that also done already early in database development. We did all the access to the database actually using functions. We didn't do any updates, inserts, deletes from the user code. It was also select from function, which is the PostgreSQL syntax for calling functions in databases. So it was original decision was for security reasons, so all the user programs didn't even see the tables. It was kind of SOA or service-oriented architecture, as we found out later. But basically you had simple functions you could call and nothing else. Also it enabled me to, on several occasions, do quite large restructurings of database without any downtime for client updates or things like this. We just move the data, made sure it's up to date, and then change the function that the client called. And that was it. Suddenly everything worked faster and better. And when we started to partition database, we first used PL-Python functions, which determined on what the database to run the function, and then used PsychoPG to connect to that database and to run the function there. And after some time, we abstracted it into a pluggable language called PL proxy. And basically, you have a language for remote database function calls, and this is the simplest function. It does no partitioning. It just runs the same function that is called on another database. But the real power comes from partitioning support. It has only 4 commands. It's connect, which tells it to connect directly, or it is a pair of cluster and run. Cluster defines cluster as a set of connect strings, set of database destinations, and run takes a function which determines which one of these cluster databases is used. And if you don't give the select statements, then exact same function is called on the remote database, but you can have one simple select statement also. So basically you can do splitting. You can also use it for analytics, which means that to kind of map reduce thing, that you ask the base data from all the partitions, it runs them in parallel, and then do the final aggregation on the central one. Okay. And this is how the end thing was envisioned to run, and currently actually the functional partitioning is put back so that all the data related to one user is in the same shard again, but now the exact shard that the user data is run on is determined by the username or a hash of username. And the larger databases are actually split between a few hundred shards. So the next thing which was needed was connection pooling. We started again with pgpool, but soon ran out of its features, and it was not very nice code to extend, so Marko Greiner wrote it. When he rewrote the PL proxy, he also split out the connection pooler component. Initial implementation of PL proxy had a connection pooler built in. And this PG bouncer, and it's really lightweight. It can aggregate thousands of incoming database connections. This was actually why support for Unix sockets was added, because EP sockets can can support only 32,000 connections, because the port number is 2-byte integer. Okay, also we move some data around. Again, initially used existing thing, then wrote our own, and then at Skype we released all these as these 3 things: PL proxy, PG bouncer, and Sky tools, which is one everything else. So basically the conclusion is that you can, say, write the MongoDB in a weekend if you have powerful tools. So, but you must know your tools before. You usually can't do that part in weekend. But if you have flexible things, you can use them. If you go out of a small tool, you can use a large one. You can actually use a larger one for smaller jobs, even though it can often be an overkill. You may need to acquire some skills that you don't already have. Yes, usually what doesn't work, often making just the same thing bigger, it may be just be too big for you. And also, if you try to use a powerful tool as you use the less powerful one, then again you may be disappointed. Because, for example, you find out that something is used quite differently to get good results. Okay, that's it. Do you have questions? I also have tomorrow a talk where I speak how to make the interaction with database from Python almost invisible, so that you can do the development all from Python, and the large part of this running the code in the database happens automatically.
Yeah, I just have a small question on the new JSON type.
Yeah.
Which is built in the new release of Postgres. Maybe also on 9.1.
No, it's 9.2.
Okay.
Yes, and
we are already using JSON storing stuff in different formats because otherwise we would have to add hundreds of tables and different the same process.
Yeah.